Yeah, hello everyone. In this lecture, we will continue the previous study of inclusion and the exclusion principle. In particular, we will apply it to a typical problem called a derangement. So the formal definition is as follows: derangement of a set of n elements is a permutation I1, I2, In of the set such that I1 is different from 1, I2 is different from 2, In is different from n, and the same as a case of permutation, we are interested in the total number of derangements denoted by Dn, the number of derangements of 1 to n. So remark is, although it looks like artificial, but it turns out not. Think about in Christmas when you play white elephant gift exchange, you don't want to get back your own gift, as I did before. So you always want a derangement instead of a permutation and leave some element fixed. And this is also the case in many applications. So probably you can look for more examples in your textbook. Gift exchange. Okay. Now, just like what we did for permutations, before we study the final properties, we start with investigate the number Dn. So when n is 1, it's easy to see D1 is 0. When n is 2, so the allowed derangement is 2, 1. So D2 is 1. When n is 3, so you fix 3 positions, 1, 2, 3, and the first position takes value 2 or 3. If you start with 2, then the only allowable one is 2, 3, 1. And when you start with 3 in the first position, then you can have 3, 1, 2. So D3 is 2. And when n is 4, similarly, first one can be 2 and 3 and 4. And if you sensitive about the symmetry, you will notice that the number of derangements start with 2 should be the same as the number of derangements start with 3 or 4. Okay, so for simplicity, we look at 2 more carefully. So if you start with 2, and then for the second position, you have 1, 3, 4, 3 choices. And then for third one, you can only fill in like this: 4, 3 for the first derangement, and for second one, you should have 4, 1, and for the last one, you should have 1, 3. And similarly, you can. I suggest you to do this enumeration, manually enumeration once, to get familiar with derangements. And for 3, you have 3, 1, 4, 2, and then 3, 4, 2, 1, 3, 4, 1, 2, and then 4, you have 4, 1, 2, 3, 4, 3, 2, 1, 4, 3, 1, 2. So totally, you have 9. And then a nature question is, do we have a general formula for Dn? And the answer is we have, although it's not so perfect. You have just like an expansion. So Dn should be n factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus all the way to minus 1 to nth power times 1 over n factorial. So the proof is based on the inclusion-exclusion principle we introduced in the last lecture. First, we define the total set. So that will be all the permutations of n elements. And the subset AI is defined to be permutations A1, AN such that AI is I. So you fix ith element. And then what is Dn? Dn just a cardinality of the intersection of all the complements from 1 to n. So A1 complement intersect A2 complement, intersect all the way to AN complement. And the next we compute the cardinality of each subset appearing in the formula. So first, the cardinality of n is S is n factorial. Cardinality of A1, A2, AN is n minus 1 factorial because you fixed ith element and all the remaining ones are free. So you can view it as a permutation of n minus 1 elements. And similarly, for two intersections, you should have n minus 2 factorial. I less than j greater than 1 less than or equal to n. And all the case elements is n minus k factorial. Here you assume they are different. Okay, then recall the inclusion-exclusion principle tells you the following formula is cardinality of S minus the cardinality of the summation of cardinality of one intersection and the plus summation of cardinality of two intersections. And then if you plug in, you find it's n factorial minus n minus 1 factorial times m. This n corresponds to the fact that there are n different AI appear in the summation. And then you plus n minus 2 factorial times n choose 2. This is because this n choose 2 correspond to n choose 2 different two intersections. And then you can continue minus n minus 3 factorial times n choose 3 blah, blah. And you can figure out n factorial. So notice that this is, for example, this one. Just n times n minus 1 times n minus 2 divided by 3 factorial. And therefore, you can combine these two factors. So you can figure out n factorial. Inside, you will have 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, all the way to plus minus 1 to nth power 1 over n factorial. And a small remark, a quick remark actually, is that you will notice that except the n factorial, the inside one is quite similar to the first few terms in the expansion of the Taylor expansion of exponential -1. Recall that. Exponential -x is 1 minus x over 1 factorial plus x squared over 2 factorial minus x cubed 3 factorial. But of course, this one goes to infinity. Okay, therefore, we have the following corollary. So consider the experiment of selecting a permutation of 1 to n at random, and the event en that no integer in the permutation is in its natural position or the original position. Then, when n goes to infinity, the probability of event en is exponential -1. This is quite interesting because although for the any finite number, we don't know what's the exact difference between the difference of the number of derangement and the number of permutations. But when you look at in the limit case, then you will see it takes a definite portion. And if you still remember, a few lectures ago, we studied the Ramsey theorem and some number theoretic properties. And in that case, for example, the probability of prime numbers among all the natural numbers is 0, so it's quite sparse. Okay, this is always a good question to ask when you have some substructure in the total structure. What's the portion of it when you think about the limit? The proof is quite easy. So actually, as we said before, exponential -1 can be written down as dn over n factorial plus -1 n plus 1 1 over n plus 1 factorial plus -1 n plus 2 1 over n plus 2 factorial plus all the way. And then the probability of en is dn over n factorial. Therefore, it's exponential -1 minus all the remaining terms. And you can use a Lagrange remainder form or just estimate by hand. It's not trivial, I leave it to you. When n goes to infinity, the summation, infinite sum in the parentheses goes to 0. Okay, then if you take limit, you just have exponential -1. Okay, so far we introduced the exact formula for dm, but the problem is if you really apply it to get a result, even for the computer, it's not so efficient. So we would like to ask, do we have some other forms for dn? The answer is yes. So we have the following a few recursion relations. So first one, suppose you have dn, then dn is m-1 times dn-2 plus dn-1. This is a good formula because if you put it into computer, you only need to know, just like the Fibonacci sequence, so you don't need to know too many numbers before it. So you only need to store a few data. So here you only need to store two data, dn-1 and dn-2. And all you need is integers. Previous formula has a lot of fractions, and when you put it into computer, you should know you always use the numericals, so you will have some floating problem, not so exact. Although the result should be an integer, but when you run the computer, probably it turns back some non-integers. Okay, and we will give two proofs. So first proof, which is a combinatorial one. So suppose you have a derangement and A1 to AN, and the last one is AN, and then we split the situation into the following cases. So first noted that AN should be an integer from 1 to n-1. And case 1, that is, if you look at the position, AN's position, if in the derangement it takes value m, then we call this is case 1. So notice that here actually you have permutation of a and m. Okay, then what can we do? We can delete a and n. Oh, this is a symbol for a pair. Or if you like, let's do it in this way. Delete a and n and a n. From the derangement, then what do you have? You have 1 to A1 and 2 to A2, blah, blah, an-1 to an minus 1, and then you have, this is empty, then you have an plus 1, an plus 1, and blah blah, n minus 1, an minus 1. And it's easy to see this is derangement of 1, 2, 3 to n. Get rid of an and n. Therefore, the number of all the derangements in case 1 is dn minus 2 times, because you can choose an, you can take n minus 1 values for an, so you have such number for the number of derangements in case 1. And then for case 2, you consider a more complicated one. Suppose an is mapped to k, and here k is, here bn is mapped to n. Okay, so you don't have a permutation of a and n. You have more complicated case, and then what we do is delete the last one, delete an, and change bn to bn an. Therefore, what you have is 1 blah blah an, and here you have something k, or aan, and here you have bn, and then an minus 1, an minus 1. Okay, and it's easy to say this is a derangement of 1, 2, 3, 4 all the way to n minus 1. Okay, and you can also compute the number, and then if you want a rigorous proof, then you still need to do the following step to construct or prove the following is a bijection derangement. Here, my notation a little bit sloppy. So here actually means all the derangement of a set of n minus 1 elements or n minus 2 elements. So more precisely, we actually need to show this is a onto map. This is an onto map. Okay, I won't continue this because the second proof is more simple in the proof sense. We will have a short discussion after all the both proofs. So for second proof, you only need to plug in all the formulas. And to verify they're same, you do the subtraction and to see if it equals 0. And then you will find that after a slight computation, you will find n minus 1 factorial, 1 minus 1 over 1 factorial plus 1 over 2 factorial plus minus 1 m minus 1 1 over n minus 1 factorial plus minus 1 to n's power minus n minus 1 factorial 1 minus 1 factorial plus all the way to minus 1 n minus 2 1 over n minus 2 factorial. This is because you first subtract the third item from the first one. Okay, then you have this, and keep the second one. Okay. So the proof is simple. The remark is that, so the reason I present the first proof is usually that's how people find or discover the formula is by first proof. Usually we just step into the problem by most naive way and to see if you can get some information. And from the first one, you can make the conjecture that the property holds, and then you turn back to look for some simpler way to prove it. So that's the usual way we do research. We use some very stubborn, very naive way to discover something. But when you present it, you choose a different way. It's clear, but it's not the way you really discover it. That's a typical situation when you read the papers, journal papers, or textbooks. They present a very clear proof, but that's not how they find it. They are cheating. Other people like it. People like cheating. Okay, next. So that's another point of view I have for mathematical objects or CS objects. Usually, the interesting stuff is the ones who has a lot of relations inside it. But you can never exhaust it. Just like prime numbers, you can make a lot of conjectures. They're all very interesting, but you can never just exhausting all the interesting properties. The more you look at it, the more interesting it is you can find. So that's a good abstract, the good research study. So here, for Dn, from that formula, you can abstract another relation, induction relation. That's a Dn equals n times Dn minus 1 plus minus 1 to n's power and greater than or equal to 2. For this one, I don't have any idea so far for combinatorial proof, but the mathematical proof is quite simple. You do the subtraction and everything cancels out perfectly. Okay, next we are going to generalize derangement to more complicated problems. But first thing, whenever we do generalization, the first thing we should do is give a nicer representation or nicer interpretation of the problem you have. If you stay in the old formulation, you can never do generalizations because you don't see a deeper structure therein. So first thing is to give a different interpretation. So we have the following graphic interpretation. So for example, when n equals 5, what is a derangement? So derangement is one-to-one onto up. You have bijection between derangements and non-attacking rooks on the chessboard which are not in the forbidden position. So here the forbidden position is diagonal. As soon as you have this nice interpretation, then you can easily generalize it. Why you should put the forbidden position only in the diagonal? Of course, you can put it in some other places. For example, you can put it in this way and ask how to place 3 non-attacking rooks in the chessboard with forbidden positions. Forbidden positions, it means you don't put rooks inside. And here seems like you only have, let's use the red circle. Oh, sorry, the blue circle. You only have one possibility. Here should be a rook, here should have a rook, and then the last one should be here. This is empty. You cannot put it into these positions. So that's an example. And next we can rigorously give a formulation. So let x1, x2, xm be possibly empty subsets of 1 to n. We denote by p x1, x2, xn, the set of all permutations I1, I2, In of 1, 2, 3, 4 all the way to n, such that I1 is not in x1, I2 is not in x2, In is not in xn. Okay, here, and then you use a small p x1 x2 to xn to denote the cardinality of the above set p x1 x2 to xn. And let's look at one example. Suppose the whole set, let's denote S, is 1, 2, 3, 4, and the x1 is 1, 2, x2 is 2, 3, x3 is 3, 4, x4 is 1, 4. And if you draw a graph, you have the following. I would like to draw two because later on it turns out you have two generalized derangement. Okay, it's just like a Sudoku problem, how to fill in. So you first fill in one circle here. Okay, and in the following case, you draw one circle in the second position. And the green part means you cannot put anything inside anymore. And then you have circle here, and the blue one here. Okay, and oh, sorry, I missed one block. Here you also have one block here. And you have blue circle here, blue circle here, grass here, and grass here, circle here, and circle here, grass. And if you write down the number, then the permutation will be, the first one is 3, 4, 1, 2. The second one is 4, 1, 2, 3. So small p is 2. Okay, then a natural question is, what is the general formula for small p? This is a more general question, but it's more difficult. And actually, you don't have a clear formula for arbitrary. So, sorry, here's xn. For arbitrary subsets x1 to xn, the reason is clear because you don't have any fine structure. Look back the previous derangements, why we can have a nice formula, because the forbidden position has some geometric meaning. It's a diagonal. And whenever you have some patterns, for example, you have some blocks in the diagonal or some symmetries, then you can expect maybe you can have a nice formula. But in general, you don't have that, except in the limited case, if you have very sparse forbidden positions or very dense forbidden positions, you might expect a nice formula. That's also a general situation in other problems in computer science. In general, it's very hard to diagonalize a big matrix, just like when you do Google search, how to organize the data. It's very hard. But if you know the data is very sparse, it's a sparse matrix, then you can have a lot of tools. You can have a lot of tools to use. And usually that's also the assumption people put on the problems. It's just keep in your mind, whenever you have difficult to search for something, look for some special property. Do you miss some properties, or in your real life, do you really have such general questions? Usually in our real lives, we have nicer questions. They all have symmetries, or not symmetries. They all have some kind of special properties. Actually, as I said before, we human beings are very special. In the universe, the condition is very restrictive to have human beings. So we are just a mystery or a miracle. So when you do research, you also should have some kind of this mind. Okay, and on the other hand, it's easy to write down the general inclusion-exclusion principle for it. And all we would like to do in the following is simplify the intersections, the coordinate intersections a little bit. So for example, what is the coordinate of AI1? That will be the coordinate of xi1 times n minus 1 factorial. Okay, oh, sorry, I haven't defined what is AI. AI is in xi. Note that if AI is in the set xi, then all the other elements can be chosen from the remaining n minus 1 columns. So you have n minus 1 factorial. And how about two intersections? And for the two intersections, it's more complicated because AI1, AI2 are not independent. So you should choose so by definition, this is the set of all permutations such that AI1 is in xi1, AI2 is in xi2, and you can compute it in this way. First, choose two non-attacking rooks. The rooks whose the forbidden position in the rows of the forbidden position. And after you choose such two numbers, AI1, AI2, then all the remaining ones are free. So you have n minus 2 factorial. Okay, and we can call the first factor, we can define the first factor as R2. So this is a number of, you should sum this up because so far the number is still depend on the column you are choosing. But if you want some clear formula, you don't want the information of the column. So you can sum this up since you have n factorial, n minus 2 factorial as a common factor, so you can factor it out. So this will be the summation of the first factors in front. Okay, and if you want some wording. So R2 is a number of ways putting two non-attacking rooks in the forbidden positions. So here you see you don't have any restriction from the columns, whereas the where is the rook located? It's not important. It's not contained in the definition. And similarly, for any K intersection, we can define a number Rk. This is invariant. It depends only on the graph. So here Rk is a number of ways to place K non-attacking rooks on the M by M chessboard, where each of the K rooks is in a forbidden position. So here K is from 1 to N. And then you can simplify the formula for small p x1 to xn as n factorial minus r1 n minus 1 factorial plus r2 n minus 2 factorial plus minus 1 rn. And then the number r1, all you need to do is figure out the number r1, r2, rn, and those numbers are more of the combinatorial flavor. But I should mention, this method is efficient. Oh, I should make a remark. The formula is efficient if the forbidden positions are sparse, not so many. Otherwise, it's a difficult problem to check the numbers. Just like if you are in a forbidden position, then it's quite easy to check the numbers. For example, remark 2. For the diagonal ones, so what is R1? R1 is n choose 1, R2 is n choose 2, Rn is n choose n. Therefore, you plug in, you have the formula. Okay, so that's the reason why we introduce this. Okay, next let's look at some not so nice example. So first one, you have a 5 by 5 chessboard. And I just randomly cross out some blocks. And for simplicity, in the we use some numbers to index the positions 1, 2, 3, 4, 5, 6, 7. Okay, then what is R1? The number R1 is just a kinetic or set 1, 2, 3, 4 all the way to 7. And what is R2? So how to choose two non-attacking rooks in the forbidden positions? So you can enumerate in the following way. First, if you choose 1, then you can have 3, 5. You cannot choose 2 or 4 because they're not non-attacking. 1, 4, 1, 5, 1, 6, 1, 7. And then you have 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7. Then you have 3, 3, 4, 3, 5, 3, 6, 3, 7. And then you have 4. 4, you have 4, 6, 4, 7. You have 5, 5, 6. That's it. So totally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So totally you have 16. And for R3, similarly, you can enumerate them. You have 1, 3, 5. You cannot choose 1, 2. So the least numbers you can start with is 1, 3. Just like a lexicographic ordering. 1, 3, 5, and then 1, 3, 6, 1, 3, 7. Then you have 1, 5, 6, 2, 3, 4, 2, 3, 5, 2, 3, 6, 2, 3, 7, 2, 4, 6, 2, 4, 7, 2, 5, 6, 3, 4, 6, 3, 4, 7, 3, 5, 6. Totally you have 14. And then for 4 non-attacking rooks, you have 1, 3, 5, 6, 1, 2, 3, 4, 6, 2, 3, 4, 7, 2, 3, 5, 6. You have 4. And you don't have any 5 non-attacking rooks. Okay, so leave it to you. Verify each cases. I suggest you at least to go through the details here because you can have just a direct feeling what the difficulty is and how difficult it is when you have not so nice structure. And as soon as you figure out this stuff, then everything should be easy. You just view them as coefficients plugged into the general formula. Another way is you can put in non-attacking rooks directly into the non-forbidden positions to track it. But when you have sparse forbidden positions, it seems like it's easier to start with the forbidden positions. And next, suppose you have 6 times 6 chessboard, and you get rid of thicker diagonals. You just thick the diagonal a little bit, or just diagonal of 2 by 2 blocks. And then you can also do the enumeration, but because of time, I would just write down several numbers. Okay, and a natural question, actually it's a very good question. Can you find some pattern for such graphs? By such graphs, I mean actually you might have the following cases. You don't need to assume it's 6 by 6. You have 2n by 2n, and the forbidden positions are 2 by 2 blocks. Can you find some pattern? Or more explicitly, can you compute P? I don't know the answer yet, so it's a good research I shouldn't say research problem because probably people already know the number or they already have some result, but it's a good exercise anyway. Okay, next. So far, you might have a feeling that all the kind of derangement, like generalized derangement problem can be put into this way, the graph interpretation exerting all the problems, but I would like to see this is not the case. You might have some, I call the nonlinear restriction, just like the following. So carousel has 8 seats with distinct colors, and 8 children are seated so that each child faces one child's front. And the question is, in how many ways can children change seats so each faces a different child? Just like the children, when you sit down, the children can only face the front, and he or she may be bored or looking at the same person all the time, so they want to have some change. Or if you don't like this scenario, you can view it as people are dating, so they open a window for the diagonal positions. Okay, and mathematically, we just let S be a set of 8 elements, and permutations, or A1, A2, A8 permutations. And so firstly, we noted that the coordinate of S is 8. And the restriction is A1 minus A5 is different from 4. A2 minus A6 is different from 4. A7 minus A3 is different from 4. Similarly, A8 minus A4 is different from 4. And A1 is all permutations such that A1 minus A5 is 4, and A2 is set of all the permutations. A2 minus A6 is 4. A3 minus A7 is 4. A4 minus A8 is 4. And the bottom line is, at least we can apply the exclusion principle. This principle holds for all the cases. As soon as you can set up, okay, then for the cardinality of one intersection, because you can first fix A1, and then automatically you have A5. Okay, then the remaining you have permutation of 6 elements, so 8 times 6. And similarly, for 2 intersections, you can first fix one element, for example, A1. Okay, then you automatically fix A5, and then you fix A2. You have 6 choices, and automatically you have A6, and remaining you have 4 factorial. And similarly, you can compute triple intersections and quadruple intersections. Okay, and notice that here, this is a special case that intersections, the cardinality of intersections, only depend on the number of sets appear in the intersection. So you can apply the formula we introduced in the last lecture. So so here, 4 choose 1 times 8 times 6 factorial plus 4 choose 2 times 8 times 6 times 4 factorial minus 4 choose 3, 8, 6, 4, 2 factorial plus 4 choose 4, 8, 6, 4, 2, 1 factorial, blah, blah. Okay, I will stop here and